Hi, I'm Sophia. I'm an undergraduate at King's College London, and this summer I've been lucky enough to be an intern with the International Space Elevator Consortium. As you can see on the screen, I've been looking into the methodologies for mitigating risk to the lower reaches of the future Earth space elevator. And in particular, I've been focusing on the risks to the tether. I'm sure everyone here will agree that space elevators will revolutionise the space sector. But there are so many things that could go wrong with it. It could overheat, be struck by lightning, snap due to high wind speeds, be corroded by atomic oxygen, be warned by its climbers, break into, and the list goes on. But in my report, I've focused on these particular issues and how to overcome them. So let's start with overheating. Heat can be gained by the tether through radiation from the sun and through friction from the climbers. Both carbon nanotubes and single crystal graphene, two of the main candidates for the tether material, have very high melting and burning points, so this doesn't seem to be too much of a risk. While there are studies that show things such as carbon nanotubes igniting when photographed with flash, there is not enough evidence to say that this would be a significant risk to the space elevator, nor that similar results will be seen by heating the tether, as there are other studies which show that carbon nanotubes are very good at being used as a cooling system. Moreover, we know that we need oxygen for material to burn, and so the risk of space elevator fires, at least above the Earth's atmosphere, is negligible. The real issue is the change in temperature that the space elevator would go through during an orbit of the Earth. At some points, the space elevator will be in direct exposure of the sun, where it may be exposed to temperatures 393 Kelvin, while in the shade of the Earth it might cool down to 173 Kelvin. This significant variation could cause the tether material to expand and contract, and could possibly cause fatigue failure, much like when we stretch a rubber band too much and it loses its elasticity before breaking altogether. And so now we move on to risks caused by weather factors. A direct hit from lightning could send 30 kiloamps and 100 million volts down the space elevator, inevitably damaging it. If we look at other tall structures such as skyscrapers and telephone masts, the one precaution used is a grounding wire, providing the path of least resistance to the ground. Similarly, rockets, planes, and boats use antennae to redirect lightning strikes away from them. But the space elevator itself is going to be the tallest object in the sky, and whether it's made from single crystal graphene or carbon nanotubes, it will be highly conductive and thus provide the easiest route for lightning to the ground. So if we were to have a land Earth station, the tether would ground the space elevator itself. If we have an ocean-based Earth station, the water would conduct the lightning to the ground beneath and still ground it. However, it may also electrocute anything in the water nearby. This would mean that no marine life could be sustained here. Thus, the best option would be to build the space elevator in an area where there's no or very few lightning strikes. One possible location which has been identified is 1,500 kilometres west of the Galapagos Islands. This also happens to sit on the equator, allowing for geosynchronous orbit and avoiding Coriolis force. Wind could also be problematic, as it could displace the tether and even sever it. Bradley Edwards, in The Space Elevator, writes that the tether could safely be displaced by up to 10 degrees from its normal, and that a ribbon made from 1,200 fibres of a 10 micron diameter would break at a wind speed of 116 kilometers per hour over a 1 kilometer segment. In order to minimize the force of the wind on the tether, we would need to minimize its surface area. This is where a rounded tether instead of a ribbon could be favored, as the wind would pass over the tether in a more streamlined fashion. We could also have a structure with holes in it, kind of like a knitted jumper, so the wind could pass directly through the tether. However, this may come as a trade-off with structural stability. Edwards also mentions that drag seems to increase in areas where composite materials are used. This would be because microscopic holes are being filled, and so naturally we should avoid this where possible. Once again, we must also pay close attention to the location of the space elevator, choosing a place where there is low wind speed, and hopefully avoiding the problem altogether. Luckily, the location west of the Galapagos Islands, which we saw in the last slide, also tends to have low wind speeds, and because it's on the equator, can't sustain hurricanes. Another concern is the corrosion of the tether. Carbon, whether it's in the form of single crystal graphene or carbon nanotubes, doesn't tend to corrode when exposed to oxygen molecules, but would bond to atomic oxygen. This can be found in LEO, between 60 kilometers and 800 kilometers, with the highest density being around 100 kilometers. During NASA's Long-Duration Exposure Facility mission, it was observed that the carbon fibre epoxy composites were etched at rates of 1 micrometer per month by atomic oxygen, which, if we applied to the space elevator, would destroy the ribbon in a matter of weeks. Exposure to radiation would increase the rate of corrosion by applying thermal energy, which would help carbon and atomic oxygen bond. NASA, in their report on space elevators in 2000, suggested coating the tether in non-corrosive materials such as gold, platinum or nickel. However, this would add substantial weight to the space elevator and would mean that despite using nanomaterials, we would still have a high tether-taper ratio. So instead, it makes sense to look beyond carbon nanomaterials into things such as boron nitride nanotubes, which don't have any partially filled electron shells on their surface, and so cannot bond to atomic oxygen. Climbers, while being an integral part of the space elevator, can also cause risk to the tether. There are so many possibilities of what the space elevator climber could be. No matter which design is chosen, it will have to exert pressure onto the tether in order to push themselves upwards and stop them from sliding on their way down. This can cause the loss of single atomic layers, which could lead to the eventual degradation of individual tether fibres. So to minimise this, it's important to ensure that the quality of the tether produced is exceptionally high. Companies such as Boeing and Texas Instruments use the Six Sigma technique introduced by Motorola in the 1980s, whereby 99.99966% of products are produced without defects. But for our tether, that would still be around 35 kilometres worth of defect. Therefore, we'll need to refine manufacturing processes even further. When spinning nanomaterial fibres, it's important to make sure that there is enough surface area contact so that the entire structure is strong, not just the individual fibres. To avoid wear, we may also need to reduce the amount of friction between the tether and the climber, possibly through the use of magnets. Any damage created, however, we would assume to be small, and therefore could repair it regularly using maintenance climbers. At middle Earth orbit, geosynchronous orbit, and super geosynchronous orbit, there is the threat of large satellites and meteors colliding with the tether. If this happens, it's likely that the tether will sever. We will be able to alter the orbits of any active satellites which may collide with the space elevator before it's even built, and we can use oscillations of the tether to avoid any other large space objects with the help of simulations. While the probability of a collision occurring at these heights is very low, it is still very much a possibility, and we should be prepared for such an event. By attaching thrusters at the midpoint of the space elevator, at GEO, we would be able to keep the space elevator in its place, as opposed to having it fly off like a mass at the end of a piece of string being spun in circles. This would make it much easier to perform any repairs and ensure that we don't lose part of our space elevator. We would already know that this position is not in any other orbital paths, and we could also have the option to reel in the tether until we're ready to proceed with any repairs in order to avoid any subsequent collisions. At LEO, only approximately 5% of the 6,000 objects orbiting the equator are operational satellites, and there is significantly more small space debris. Only bodies larger than 10 centimetres are tracked in space, which means we're blind to anything smaller. This means that we're unable to avoid them by oscillating the tether because we don't know where they'll be. Thus, we need to ensure that the tether can withstand smaller impacts without severing. This can be done by having redundant lines in its structure. These are non-load-bearing fibres, which will only take on load if a primary line is cut. We would be able to monitor smaller cuts using scanners attached to climbers, which could potentially give us a 360-degree scan of the tether every other day to identify smaller breaks. Then, we could send out a maintenance climber to carry out repairs when there are enough cuts, but before the tether severs. This would be much more practical than having a maintenance climber in a regular climber cycle, as it would add more weight to the space elevator and not necessarily always have something to fix. If there is sever at LEO or below, we may not even need the thruster system, as discussed on the last slide. Instead, we could reel out more tether fast enough so that the space elevator remains stationary, and it could be reconnected to the Earth station without having to wait 3 months for repairs to be carried out. This would require significant amounts of extra tether to be stored at the apex anchor, but from a commercial point of view, may cost less than a business loss in the 3 months where the space elevator is inactive. So if the tether does break in two, how can we bring it down safely? The actual tether will cause minimal damage as it falls, because it'll be made out of very light material, and therefore is likely to fall very slowly and have a small impulse on landing. We could design it to burn up on re-entry. However, this would mean that we could lose a lot of expensive material and pollute the environment with disintegrated nanomaterials, which doesn't seem ideal. Alternatively, we could attempt to catch the tether as it falls using drones. This would allow us to bring the tether down in a controlled manner, or even hold it up so that it can be reattached. It is also possible that a climber could be attached below the sever, which would add significant weight to the falling tether, speeding up its descent. In this case, it may not be possible to catch the tether. However, we could still bring it down safely by attaching parachutes to the climbers. If we had an ocean-based Earth station, the climbers and their cargo would fall safely into the water, and we could even recover them. So that was somewhat of a whistle-stop tour through what can go wrong with the space elevator. But perhaps it's reassuring that we can find solutions to all of these problems. Thank you for waking up so early to listen to my presentation, and I hope you enjoy the rest of the conference. If there are any questions, please feel free to email me at sophia.lee_roberts@kcl.ac.uk, and I'll try to respond before the end of the weekend. Thank you.